It's a great honor to present in this developers meeting. I am Jaeyong from the affiliated Institute of L3 in South Korea. Our team is interested in analyzing multi-CPU binaries. I am in charge of the LLI-related development in our team. The topic of my talk is about the execution domain transition in LLI. Precisely speaking, our method improves the performance of LLI's interpreter mode. I'd like to share our experiences about the hurdle we found and how we overcame it in this presentation. This talk starts with the background explanation and the definition of what we call the domains. And then I will talk about our major proposal, the execution domain transition. Finally, I will wrap up this presentation with experiment, result, and demo using short video. Analyzing malware requires deep understanding about CPU architecture. To make matter worse, when it comes to IoT malware, they are targeting various CPU architecture. For example, Mirai, one of the most infamous IoT malware, was opened its source code 6 years ago. And it can be built on 10 CPU architectures. The variation of Mirai are still attacking IoT systems today. However, it's very hard for a single analyst to be an expert of diverse architectures. Most analysts have not knowledge about every CPU architecture. Also, preparing execution environments for each architecture requires a lot of money, time, and effort. There are huge costs to build all virtual machine environments, so we focus on LLVM IR as our singular analyst language due to its CPU independence. So we will analyze binaries using CPU-independent IR. Our single host platform is targeting multi-CPU binaries, but for better understanding, this presentation focuses only on Intel host or ARM binary. As we already know, in general, we can emit LLVM IR using source code. In this case, the IR has to contain correct high-level information such as the function boundary, local variable types, and the exact target range of indirect control flow. In other words, we can say that the symbols for representing target and its execution are sufficient. This slide shows an lifted IR from binary by our lifter. As you can see, it looks more complicated compared to the previous IR. Basically, the binary lost many high-level information during compilation. So for lifter, these losses are the challenge, and the lifted IR instruction represent the behavior of machine code, not the one of high-level semantic itself. You can see that the semantic is represented through the I/O to the registers and memory. Machine code consists of explicit and implicit expressions. When all representations of binary are made into IR, it can be executed dynamically. And if the state resulting from the execution of one instruction is stored in a virtual space rather than a real machine, it will be possible to run multi-CPU binaries on a single host. So we want to store the dynamic execution state or IR in virtual CPU and stack. We had implemented a cross debugger based on this IR using LLI in 2020. After this slide, please note that The LLI is the one we modified it for lifted IR interpretation. In fact, we found a problem using the LLI in its practicality. LLI takes too long to reach the desired location of code. We analyzed why and concluded that lifted IR is root cause. Lifted IR contains all sorts of the information about execution, such as CPU state variation and side effects. For example, the figure below shows that 4 machine codes are lifted to 19 IR instructions. Let's assume that we interpret a load instruction. To interpret load instruction, the visit load function is called. You can imagine how much machine code needed to be run when LLI code is compiled. So to emulate one line of assembly code from an original binary, tens to thousands of assembly lines should be executed on the host. As a result, accumulated overhead causes huge time consumption. We did experiments over 100 times to measure running time of the binaries. We used Linux core utils binaries for test. These are the results of a comparison of running time. The left side of the slide shows the results of original binaries execution. And the right side of the slide shows the result of LLI. We distributed binary into 3 groups based on running time. You can see the remarkable differences in the C group. Even in A group, which consists with simple binaries, also shows slight delay when binaries run on LLI. This video shows the execution of our LLI. The target binary is ls command working on ARM Linux operating system. This binary lists directory contents. We will show demo. The left side, the video shows default execution. Then the right side shows function calls in default execution. If you have ever used the ls command on a Linux console, you will notice how slow it is. Now you can see just how slow it is to run with LLI. The alternative for running time overhead was the rewriting binary for host platform. So we compiled the lifted IR, and it emits rewriting binary. Even if the original binary CPU architecture is not the host platform CPU architecture, it can be compiled due to CPU independence. And of course, this rewriting binary also uses virtual CPU and stack. This slide compares the running time of the binaries. Left side is the running time of the lifted IR on LLI. And the right side is the running time of the rewriting binary. For sure, the running time of the rewriting binary is similar to the running time of the original binary. Although LLI is slow, it has great advantages in analysis. For example, we can IR with optimization, such as symbol recovery or function boundary recognition. We can analyze by more readable code while running in LLI. And although rewriting binary is fast, it is quite not easy to be used in IR analysis. Those two have the same data storage in common. So we tried to take both advantages. To do our goal, let me define the terminology of host execution and target execution. Host execution means the relationship between host platform and target method like LLI or binary. In the host execution, LLVM IR can run on LLI, and in the form of rewriting binary using stack and CPU of the host. Target execution means the relationship between target methods and the virtual storage. It is possible to emulate any kind of CPU by storing the state in the virtual storage. Look at the right side of the slide. LLI and rewriting binary are loaded in one process. We made them to share the virtual storage. Whether it is executed on LLI or as binary, the state is shared. We call IR and binary two closed worlds. For one process, those two run on self-contained worlds. So the IR and binary domain execute for each enclosed world. Our idea is to tear down the world and connect two worlds. When LLI executes main lifted function, the execution jumps to the binary world and executes the function in machine code. This is enabled to take benefits of the other closed world using domain transition. From now on, I will explain in more detail. LLI has shared the data storage for virtual state. First, LLI collects symbol information from rewriting binary. A symbol table entry is consists of symbol name and symbol address. Second, LLI finds the virtual CPU address of the rewriting binary and stores it in the execution engine of LLI. This information is used when the execution engine of LLI calls the emit globals function. Emit globals function allocates memory for global variable for parsed IR modules. In this function, LLI creates the virtual CPU in the heap. Since the virtual CPU is defined in the IR, LLI employs virtual CPU in heap, and rewriting binary use virtual CPU defined at the data section of the binary as a symbol. This is why LLI and binary are isolated from one another to their own closed world in target execution. We need to isolate those two and share the data storage about the virtual state. So we should set the LLI's virtual CPU address to the one we saved in execution engine a little while ago. Now, the LLI world and the binary world share the same virtual state. And then I will explain to change program counter. Domain transition is done by functions as a unit. This means that domain transition is permitted only to transfer each domain by entering the function. Since there isn't an easy way to rewind the stack in the middle of the function. To enter binary from the LLI domain, we need the name of the function. So from the LLI's existing called function, we check the function name. During the binary lifting, we already create a mapping table of function name and each address. By using this table, we obtain the function address. Even if the function symbol is stripped, we did some research to find the function boundaries. So we assume that we already know the address of the function entry. After LLI obtains the function address, it stores the RSP and RBP register of the real machine. In target execution, the registers to be used in function call convention or already ready in the virtual register. So all we need to do is modify the PC register to the address obtained from the mapping table. Parameters required for function call in target execution are already reflected in virtual CPU. So when LLI jumps into binary world, you only need to know the address of the lifted binary code. Then execution in rewriting binary code. When binary encounters a return instruction, it returns to the LLI world. Then LLI restores RSP and RBP register. Since the binary world also uses the same real machine, RSP and RBP registers. Now I will explain when execution transfers from binary to LLI. First of all, in the initialization process, LLI parses the IR module and does the execution engine initialization. And also, LLI saves the trampoline function address to designated global variable of binary which was ready in the binary rewriting process. Now, the execution proceeds from the binary world to a certain function in the LLI world. The function is resolved to be transferred to LLI world. The binary dives to the trampoline function of LLI, referring to the global variable. Now we are in the LLI world. We can get PC value from the virtual CPU. Then get the function name from the mapping table inversely. Each stack means execution context stack. LLI updates function execution information to each stack. LLI creates execution context structure using the function name. In the LLI world, LLI iterates the each stack until the size condition is met. In the iteration, LLI visits IR instruction. If the size of each stack is reduced, it means that the function is executed. Then the execution is returned to binary world, and execution proceeds to the next instruction. This is our experiment result. This result shows the running times of LLI only with domain transition. We conducted tests on core utils for 100 times each, and this is the average number of all tests. The maximum range that the domain transition can be applied to is the main function. Applying domain transition in the main function achieves the best performance. By applying our technology, there was a maximum 99.82% reduction in execution time. Especially Group C had frequent file sorting and looping. We can solve the accumulated overhead of the repeated IR execution by using domain transition. From now on, I will start a demo. These two videos show before and after applying domain transition. I applied the technique on the main repeat function by proceeding execution on a binary wall. We could fast forward the running time until the default execution in the left side video was completed once. The execution of LLI applying domain transition in the right side video was executed 9 times. The running time of LS program shows average about 0.3 seconds when applying the domain transition. Next, the video shows entering the binary world for analysis. You can see the execution is now entered to the LLI world from memory allocation function. Now let's set the breakpoint. By trampoline function, execution is suspended after it enters the LLI world. You can see the local variable. As you know, % means the local variable. After % number 2 is executed by single stack command, the pointer type value is stored in the local variable. You can see the virtual CPU. As you can see, there are register variables in the virtual CPU. This is the end of our presentation. Thank you for listening.
Thank you very much. Thank you, John. Do we have any questions?
Hello, thank you for the talk. I was wondering, basically, this is like an emulator you're building. I was wondering, like, what are the limits of your emulation? Like, you know, if you compare it to an actual hardware, did you see any differences? Like, you know, how faithfully can you emulate it? And in particular, do you do anything about signals?
Since I'm not familiar with speaking using English, I may have misunderstood your question.
Okay, so I'll try repeating. Basically, is there any difference between executing the binary on real hardware and inside your environment? Like, what are the limits of the emulation that you do? Okay, we can take this up afterwards, I guess.
So please email me for details here. Sorry.
Any other questions? Okay, then let's thank Janko for his presentation.